Hello, welcome to my presentation about solutions for fluorescence microscopy in biophotonics. I'm Simon Kempf and I'm a sales engineer at Laser 2000. First, let me tell about a few words about Laser 2000. Laser 2000 is located in Wesseling, and we have more than 30 years of experience in all facets of photonics. We work with manufacturers from all over the world to provide our local customers with their products. And for this purpose, we not only have contacts in Germany, but also in France, the Iberian Peninsula, and Scandinavia. And also we have some partners in the UK and in Benelux. For us, it's very important to consult our customers in every stage of their project. In this way, we create a basis for comprehensive individual solutions that respond to every project, no matter how special the project is. And our wide range of products allows us to develop solutions for almost every demand. But now, let's come to the topic. What I show you here is a schematic setup of a fluorescence microscope. You have a white light source, or a light source in general. You go through some excitation filter, reflect, in this case, the blue excitation light with a dichroic mirror onto the sample through some focusing optics. And then we have the fluorescence light with a longer wavelength, which is going through an emission filter and the dichroic mirror to the detector on the top. I don't focus on the detector today. It's different for different topics. It can be a camera, but it can also be a photomultiplier or a SPAD. For the filters, it's important to exclude all background light. You have a filter in the excitation path here on the left, where you need a small bandwidth because you just want the small bandwidth to excite your sample. And what I show here is, for example, a SAMROC filter. It has this steep edge, which is really unique from SAMROC. So you can select, for example, 488 nanometer, which is a very common wavelength, and you get only this light to excite the fluorescence. And what they have is emission, on the other hand, which is going to the detector, and therefore you use a filter, a bandpass filter, to the longer wavelength range. But also here it's important to block all the background noise from your detector, and you need these sharp edges and this narrow bandwidth. Same applies, of course, for the dichroic mirror. An important thing where I focus now is the light sources. Historically, white light sources are used, for example, xenon arc lamps or mercury vapor lamps. But nowadays, you get these high power lamps with LED light sources. And there I want to show you a very good solution from our partner, Blue Box Optics, Lenici. And Lenici is one box where you have up to 7 wavelengths in one box accessible. So you have only one interface, and you can use all the light sources together, or you can just address 1 or 2 of these wavelengths. It offers solutions from 380 nanometer up to 730 nanometer, and you have the optional light guide, which makes it easy to integrate the light source into your microscope. And what you can see here on the left bottom corner, that you have a very wide wavelength range, which covers almost every fluor for your microscopy application. But nowadays, often you do some scanning with the microscope. You don't only have the dichroic mirror, you use a laser spot where you are scanning over your sample, and then you detect it, for example, with a photomultiplier, and you create the image with some intensity, where you put the intensities of the fluorescence light together to the image. And therefore, one uses diode laser, solid state laser, or in case of multiphoton microscopy, femtosecond lasers. For this purpose, we have a partner, Oxius. Oxius offers low noise lasers, diode lasers, and DPSS lasers. They have a broad wavelength range from 375 nanometer up to 1064 nanometer with a good beam shape and powers up to 500 milliwatt. If necessary, there are also narrow bandwidth versions available, SLM lasers. And you can use fiber delivery, which also is great for the coupling with the microscopes. What we often have here is that we have customers, they have, for example, a multiphoton, a confocal microscope, and they ask us for 3 different wavelengths or 4 different wavelengths. And what many of them don't know is that Oxius has a one-box solution for this purpose. So you don't have separate beam paths for the 3 wavelengths or 4 wavelengths. You have a one-box system with space for up to 6 lasers at different wavelengths. And also you have options such as an AOM. You can decide which fiber coupling fits to your microscope, or if you want to have a free space output, or also 2 outputs are possible here on this side. And this is really easy to integrate into your system, especially for confocal microscopy, flow cytometry, and Raman spectroscopy. And now I show you some solution for multiphoton microscopy, where you excite with a longer wavelength and you get a shorter wavelength fluorescence. And therefore, most of the users still are using these bulky big Titan sapphire lasers, which needs a lot of space on your optical table. And what you can see here on the left is a typical power curve of this tunable laser. And you see here is the peak at 780 nanometer. There, the laser offers the power peak. And the partner Spark Lasers has seen that many of the users, they have these tunable laser, but they just tune into one of the common wavelengths, 920 nanometer, or 1 micrometer, 1064. And what you can see here, the 2-watt version of the femtosecond fiber laser has already a bit more of power at 920 nanometer. And there is also a 4-watt version available, which has, of course, much more power. The effect is even more at the 1064 nanometer laser. And therefore, they developed this small system, the Spark Alcor laser, which doesn't need a lot of space on the table and is easy to handle. It's available in 2 wavelengths, 920 nanometer and or 1065 nanometer. So you have a dual version where you have 2 separate laser heads. They offer up to 5 watt of power, and they have a pulse duration of less than 100 femtoseconds. Compared to the Titan Sapphire laser, it has a very low maintenance. There is very low maintenance. And what they also have, they have an integrated AOM in the laser head. So this is the new version where it's integrated here in the front. Below is the old version where it was in front of the laser head. And with this AOM option, you don't need a pocket cell for your beam path in the multiphoton microscope setup. And what is really unique is that Spark offers a fiber delivery option. Nobody else does this. And so if you have a confocal microscope, for example, with a fiber coupling, you can couple the fiber directly into the microscope and upgrade your microscope to a multiphoton one, which is really nice. And a big advance is also you have a plug-and-play laser. On our YouTube channel from Laser 2000, we have an unboxing video of this laser, and it takes about 6 minutes to unpack the laser and get it running on the optical table. So this is really an advance compared to the Titan Sapphire laser. I think it's not the alternative for every user, but if you're thinking to have a second system, or if you always work with the same wavelengths, you should really think about using a femtosecond fiber laser from Spark for your second system. Okay, thank you for watching. I got one question. Is there any LED white light representing the solar spectrum? I can answer it later, but there's not any LED. You need, different LEDs. But I think I will contact you later to provide you some solutions which you can do to provide the whole, to cover the whole solar spectrum from UV to IR. Then thank you for watching, and if you have any request for some lasers, especially for biophotonics, but also for other applications, please contact me at our virtual booth.